Okay, let's get started. Let's go over the basics before diving into the lecture. Just to be clear for those who are new here, we are called Big Data Demystified. It's a community for data professionals such as yourself. My name is Omid Vahdaty. I'm the founder of this community and founder of Jutomate. Today we're going to talk about an architecture of petascale and using several technologies. This is part 4 of a series of lectures on this topic. All the lectures are uploaded here to our website under the section of data engineering architecture. Over here you can see my first lecture, my first architecture, Petabyte, sorry, too excited. My first petascale architecture. I'll put here the link in the chat for those who want to catch up. To everyone, go. And as for the meetup, if you're not registered, I would be honored if you would. This is the link for the international group. We are worldwide active in several countries. We have about 15 followers worldwide, including the Israeli community and other communities as well. What I'm going to do today is continue our lectures. Previously, we had in session 1 introduction session and the video slides over here. And then we introduced a petascale use case of sensor data, which we want to process via 10 analysts. And I will remind a little bit about that. One second. I want to open this as well. We can talk about the use case. The use case is detailed in section 1, but I'll open it. So we'll have it in front of us when we discuss. Okay. And this is pretty much everything I wanted to share with you before I get started. Any questions on previous sessions? If you happen to join, see a review, is this something you wish to share, ask before we go on? Okay, so without further ado, let's talk about the use case. Just as a quick reminder, the use case is just an example. It's not something too complex in terms of theory, but just to get us all aligned. The use case is always important when you want to build a new architecture. Essentially, when you build an architecture, you're matching a technology to a use case. If you're misusing an architecture or abusing an architecture, then naturally the results would be unintended, either via performance or via cost of your underlying infrastructure or maintenance. So to be clear, to be precise, the use case I devised is as simple as follows. It's a use case of static data, 1 petabyte of sensor data of weather. It's one table consisting of 5 columns, including timestamp, gear ID, sensor ID, value, and sensor type. All the data is compressed 1:5 ratio, meaning 200 terabyte before compression, 1 petabyte after compression. 10 analytics users or analysts are going to work full-time job against the system. Assume this data of 1 petabyte represents 3 years worth of data. Frequency of sensor data is 10 seconds, and naturally several sensors and several go. For the sake of this exercise, for the sake of this exercise, we are going to review only the infrastructure side of the use case, not the entire ETL and how to load the data, and discuss best practices around that. On sessions number 2 and 3, we went over several technologies. We discussed Redshift from AWS. We discussed Databricks, and we discussed another technology. We'll get back to me in a second. BigQuery, that was. Okay. So today we're going to cover 2 technologies and do some summary and some follow-up questions to better understand the use case, technologies, and everything related. So let's talk about Snowflake. As discussed in previous sessions, I devised some sort of a framework to be able to compare the different technologies. You should not take that as a framework for selecting a new technology for a new architecture. It's just a reference that will get you started on the right direction. Per use case, I might change a little bit the frameworks, but more or less, it considers all the relevant aspects when you go approach a new use case. So it will be a very, very good starting point. Naturally, everything here is for training purposes, so some of the data may not be totally accurate, just for us to have something to discuss and review the methodologies and the relevant jargon, how to approach things, and so on and so forth. As a rule of thumb, I welcome questions and discussions, so feel free to interrupt me along the way as much as you want. Just be sure to open your microphone so I can hear you. And you are also welcome to ask questions via the chat. It's also okay. I track it on my left monitor. But please, if you're not talking, just make sure you're muted. But you're more than welcome to interrupt. So, just a full disclaimer for those of you who don't know me yet. My name is Omid, and although I'm passionate about what I do, it doesn't make me absolutely correct. You're more than welcome to challenge me and send comments during and after, and you're more than welcome to add me on LinkedIn so we can stay in touch. That's part of my fun in this lecture, so feel free. A little bit about us, as discussed, the meetup community. We have some links here about the AWS community and the big data demystified community. About me, rich career from the Israeli high-tech industry. Lots of startups behind me, some successful, some less, but overall a very exciting career path in the Israeli high-tech. Today I work at Jutomate. It's a consulting company by me. I founded it, and we especially work with the UK market and the Israeli market and provide consult regarding architectures and anything related to data, from anything small like problem solving to long-term strategy and full data departments. I also was fortunate enough to work at some exciting media companies such as Walla News and Investing.com. I have a tendency to jump out of airplanes for fun, and I'm a third-degree black belt in Taekwondo. And I have a tendency to give away for myself a lot, to volunteer, to contribute in the community, and to lecture mainly about what I'm passionate about. So, a long time ago, everything was very simple in the past. It was only 3-tier architecture, and then came big data, and everything became more and more complex, making our lives very complicated. And on top of that came the cloud, and then the invoice, making everything more complex to implement in a cost-effective manner. The trend didn't stop there. It keeps growing. The amount of technologies is staggering, and the amount of data we're keeping it keeps growing exponentially. So my solution, my approach to this is cloud methodologies combined with big data methodologies, and that would be my definition for data engineering. Today's agenda about this is Snowflake and SQream. We'll start with Snowflake. So, as in the previous lectures, we're going to review the architecture and the billing structure, so we'll be able to compare the apples and apples. Essentially, scale-out architecture with auto-scaling capabilities. Truly decoupled, cost per second. Essentially, if I make it very, very simple for you, it's $2 per hour. And each time you want to increase your server or your cluster, you simply double your costs. Additional $2 per hour for security, and it's columnar storage. Mind you, the updated pricing is a bit more complex, a bit unclear, but generally speaking, the lowest entry point is about $2 an hour. You can gradually increase that times 2 until you hit the largest cluster available, and so on and so forth. To be clear, Snowflake prefers an insert. That means you have 2 methods to work with Snowflake. Either you take your data from your external S3 bucket and load it to a Snowflake cluster, and they themselves save it on their own S3 bucket, but it's not accessible to you. The benefits of doing so would be performance, and performance. The cons of doing that is that you are paying essentially for compute time and insert time, which is a penalty. So essentially, if we are talking about uploading 1 petabyte to the cloud, assuming 10 gigabit network interface card, generally speaking, it's a lot of time. Just a rough calculation, not highly accurate, but you get a sense. It takes time, even if you put more servers and more clusters and so on and so forth. Benefits of using Snowflake is that aggregation is essentially relatively fast, because the bigger the cluster you have, the more computes associated per small units of data, and you can work in parallel on very large amounts of data and have an effective aggregation. So essentially, sorry about that. The advantages of working with Snowflake, that it's truly decoupled and it has elastic cost, it's very fast and it's easy to get started, very simple syntax, very popular in the market. Very fast boot, minimal waste of building time, which is very good advantage compared to the competition. And it has an ability to time travel on your data, which is a nice feature for specific scenarios. Worth the note, not very popular feature on all databases, but nice to know. In terms of cost, as discussed, you have some penalty for insert time, especially when you are talking about migrating your existing petascale workload to a new workload. It's not trivial to estimate the required cluster. So essentially, most of my customers overcommit on a yearly cost for working with Snowflake. They're quite happy, but they are paying about 60% more than they should be paying. When you talk about 1 petabyte, that's a lot of data, that's a lot of processing power. It's a very expensive invoice on a yearly matter. On top of that, when it comes to embedded BI use cases, where you have performance targets and concurrency in 24/7 scenarios, it's not very cheap, because this by design was designed to be shut down every now and then, meaning when you turn off Snowflake, so essentially you're not paying. But when it comes to 24/7 cluster, that means you are paying for the entire 100% of the seconds during the month and the cluster is on. So you're kind of missing kind of the architectural benefits. Furthermore, like most of the technologies we are going to present in this series of lectures, there's the knee problem. The knee problem is associated on the time it takes to complete a query compared with the volume of data. Meaning the more data you have, the more it takes time to complete. One would expect that it would be linear. However, most technologies are built in such a way that there will be little or no difference when you increase the data. But there is a point where the time is being prolonged and becoming longer and longer to process the same amount of data, simply because the technology is incapable or inefficient enough to process an exponential growth of your data. So when you talk about the petascale use cases, one of the things you want to consider is the velocity on top of the volume. What is the rate of the new data coming into your system? A good technology should be able to process linear growth on top of your existing data set and a lot more than that. When it talks to, in terms of performance time, Snowflake is relatively good. It's not real time, again, it's designed for analytics use cases. That means you can wait a few seconds to get a response, but all in all, a very fast and very good solution. In terms of best practices, using internal storage works best naturally in terms of performance and in terms of ease of use. A dedicated cluster per use case could do the trick in some complex scenarios where, for example, on the same data set, you need a research team and some analysts and some business user to ask business questions. So you can have different workloads on different clusters using the same data, which is quite useful. And you can use an elastic approach, meaning you can set the cluster to sleep after 10 minutes of inactivity, which is quite nice and quite useful when working with the large data sets. Before I switch to the TCO analysis, any questions?
What do you mean internal storage workspace? So,
if you remember this slide, we discussed about the fact that you need to insert the data.
okay.
But specifically, Snowflake also saves the data on S3. It's just highly optimized on the reads and writes. But what they do on top of the insert is divide the data into micro partitions and I add some sort of a smart index. So essentially, when you are querying your data through the cluster, you're doing a very smart data skipping and only access the data you need.
Okay, got it. Thank you.
Good to see you, Chun, by the way.
Okay.
Any more questions? Very good. So let's switch to the TCO analysis. Again, as mentioned in the beginning of the lecture, it's just a framework. There may be other costs associated on different use cases, but the whole idea is to give you some sort of framework to compare several technologies which have different architecture, different billing sets, billing philosophy, and to be able to compare them easily. So in this case, we're talking about external storage, which would be on S3 compressed. So it will be about 200 terabytes, which roughly sums up to about 5K monthly, which is about 60K yearly. Internal storage is after the insert, where you insert data to Snowflake, also estimated to the same number. In terms of licensing, there's no special price for the pricing. Sorry. There's no pay-as-you-go scenarios because you're essentially paying a fixed price for uptime of a cluster. There's no flat rate, essentially, you need to pay because all the cost is associated with servers. So for the sake of the exercise, since there are 10 analysts, I took per analyst the biggest machine I could find, which is 6 exabytes. I used the calculator of Snowflake, which sums up to about $90,000, multiplied it by 12, which is about $1 million yearly. The fixed support number was added across the board, which sums up to 100K monthly or 1,200,000 yearly. Any questions about the TCO analysis? Okay, 1 second, please. Okay. So essentially, if we're assessing Snowflake, generally speaking, in terms of performance, relatively fast, in terms of simplicity, we have very good simplicity associated with the solution. Theft, of course, not the cheapest solution compared to the rest, but relatively okay compared to the framework. Meaning, generally speaking, you should expect per petabyte about $1 million price tag on a yearly basis. And as a ballpark, it's a relatively good estimated number. Naturally, billing differs greatly on every commercial contract you have with the vendor, But as an assessment, I would assess that this one is the most expensive overall so far from the solution proposed. Any questions before I move on to the next one? Okay. So I want to present the last technology in this series of lectures and then open the discussion if you like, go a little bit deeper, go back and discuss other solutions or anything else you wish to discuss. SQream is a wonderful solution designed exactly for petascale scenarios, and we'll talk about these in a second. So, as previous lectures, let's talk about the architecture and the building. Compared to other solutions so far presented, SQream is a scale-up solution. A scale-up solution in the past was the common practice, but the technology that offered the solution is what differs greatly in other solutions from other solutions and what solves the new problem. Essentially, it's an MPP solution which is GPU powered, columnar like every other solution, and it's designed with the Petabyte architecture in mind, meaning solving the new problem. In terms of billing, they have several plans, both fixed and pay as you go. That depends on your use case. In terms of insert, they can do both, meaning they can work externally and internally, like any other solutions. In terms of uploading 1 petabyte SQream, this is a major difference compared to competition because it's a scale-up solution. You can use one very powerful NIC per instance in your cluster, and it essentially cuts down the insert time drastically. So if you are working on workloads which must contain new amount of data and the velocity is in the petascale as well, so considering insert time might be a very good point of reference when you compare technologies. In terms of aggregation time, due to the power of GPU, the processing is so powerful that you don't need the amount of machines you need in scale out. So essentially, one GPU can replace 100 instances in your cluster. But in terms of everything else, it looks the same. You have local disk, you have external, and the aggregation is fast, sometimes even much faster than you can imagine, simply because of the power of the GPU. In terms of advantages of SQream, it's fast beyond comparison. It's very easy to get started. It has a very simple syntax, and it opens a new world of possibilities in the domain of research beyond analytics. For example, you can process data on a raw data level without ETLs, without transformations, simply because it's so fast you don't need to remodel everything. You can do ad hoc queries on petascale and get results in a reasonable manner of time and effort. In terms of flavors of deployment, it's available both on data center and cloud deployment, which is quite useful if you are in an industry 4.0, when you have to be very close to the manufacturing line and so on and so forth, and then have maybe more complex scenarios where you have a star of geographies and you need to go all the way from your data center to a central cloud. So it's quite useful. In terms of cons, like every other technology, it has some cons. There's minor penalty on insert time, like every other technology, but at least it's faster. It's not cost effective for small data sets. Unless performance targets are mandatory, and there are some use cases where a customer comes to me with a requirement that the response of the processing must be within a very short window of time, for example, 1 second, or 1 hour, 1 minute, and the amount of data is huge, and there's very large degrees of freedom. For example, raw data sets which are raw data, and then you need to enable ad hoc exploration for end users. So imagine raw data connected to a BI solution, and the end user would ask a very crazy ad hoc query, which ends up to a very expensive infrastructure unless you're using a very powerful solution such as SQream. In terms of the knee problem, if you remember, all the solutions have the inflection point where everything becomes much slower to a point where it fails and unable to proceed. I personally tested SQream for a customer on 5.4 trillion records, which is by an order of magnitude more than anything any other technology can handle easily. I'm talking about insert and then run your queries without tuning, without massaging the data, without EGL. Simple insert and select, and it works. In terms of performance time, again, much faster than you would expect, simply because the way it was designed in performance in mind for large data sets and to solve the knee problem. Best practices, like any other database, you want to use internal storage. It works best in terms of performance. You want to have a dedicated cluster per use case. That means when you use SQream, you can have several deployments, and you can also consider that as a highly specialized cluster for your workloads or research or your embedded BI. You should consider also the elastic approach when you're not using it. Any questions before I switch to the TCO analysis? Okay. As shown on the previous technologies, we have the framework here to compare. The storage is more or less the same on the external. You want to have a copy on your S3, and you want to insert the data to improve performance per ad hoc query, so you won't waste time on waiting. In terms of licensing, this is a bit more expensive than you expect, but it's been compensated by the amount of server. We're talking about one server here that will be able to handle those 10 analysts, just an expensive machine. So you immediately here see, by comparing this technology, although it's a bit more expensive than Snowflake, you are able to do stuff which you weren't able to do before, and it's much easier in terms of predictability of cost and maintenance, because we're talking about one machine. However, the downside is quite clear when you talk about such a technology which is unique and distinct, as it's not designed for very small data sets, meaning there's a entry barrier which is more expensive compared to the competition. You cannot start with $2 an hour like Snowflake or Databricks or BigQuery or whatever. However, the advantage of such a technology is when you go beyond the 100 terabytes, you don't need to increase the amount of servers because you can process very large amounts of data without changing your infrastructure and increase your cluster size year over year to get a very, very good offering if you talk about the long term and your velocity and volume requirements. So in terms of assessment, when comparing the 5 technologies, SQream also falls in very good place. Faster, cheaper, and simpler. Let's talk about summary. So if we talk about all the different technologies discussed and presented so far, you can pretty much divide them by 2 categories. Spend, which is the y-axis, and volume, which is the x-axis. Why is that important? It's important because you need to know where you stand in the coming years. So if in this use case, we are going to work on 1 petabyte and we're not going to go, so essentially a $1 million price tag is to be expected, and it's going to be more or less static over the years. And I aligned the technologies a little bit according to the spend and volume capabilities, so you will be able to understand if you increase the order of magnitude times 2 times 10, where will you stand? So essentially, if you have a 1 petabyte use case and you plan to grow in your research, BI on raw data capabilities going forward, so the more data you have, the more you're able to process, and the price tag doesn't shoots up to the roof. It's not the same for Redshift. In Redshift, the more you increase your data, you shoot to the roof in terms of performance, price, capabilities. The same goes for Snowflake. And the more cost-effective are Databricks and BigQuery, but there's a point where they won't be able to handle too much data on specific use cases. Although, just to be clear, all these 5 technologies, we are talking about the top solutions worldwide. I mean, you could not go on with any of them until a specific point. So defining your use case kind of enforces which technology will perform well and which technology will not perform well. Moreover, I would say the following. 2-3 years ago, there was a use case in this meetup where there's a customer came to talk about the success story, about what they did. They switched from a data center use case using Hadoop and Spark, and they had a team of 30 people, which are Spark professionals, and they spent about $500,000 on infrastructure, which in a sense sounds highly effective in the TCO analysis until you add the salaries. And in terms of facts on the ground, what they said about themselves is that they're spending most of their time maintaining the system instead of ad hoc research and analysis and bringing value to the company. So they tested 1 technology, to my recollection, or at least the technology they selected is Snowflake, and they spent $4 million on 2 petabytes. So essentially $2 million per peta. And they were happy, very happy. That means that sometimes defining the requirements of what you're trying to achieve is very important. And what they were trying to achieve is to focus on insights and less on maintenance. And they got the job done. The price tag was a bit expensive to my taste, but still, they got the job done. So, circling back to what we're trying to achieve as architects, our job is to match and to balance between the use case and the technology. So it all falls down to three simple concepts. This is the framework I want you to remember, not the TCO framework. It's all about balance between faster, cheaper, and simpler. So a good architecture would achieve 2 out of 3. An excellent architecture would achieve the balance between maintenance, ROI, and performance targets. But it's not always achievable, especially the more complex the use case is. That's it. Go more or less. Do you have any questions?
I do have a question. Can you go back to that cost versus the data volume slide? Yeah, on this slide, you put BigQuery, Databricks, and Amazon Redshift on the left side of the chart. So not even by the 1 terabyte mark. Do you mean that those data warehouse system cannot handle like 1 terabyte, 1 petabyte data?
All of these technologies can handle 1 petabyte.
Okay.
But since it was very hard to illustrate the problems, I was trying to exaggerate a little bit by dividing this to 4 quadrants. So essentially, there's the most efficient quadrant, which is not a quadrant, it's a line between 2 quadrants where you spend as much as you need to process as much as you need, which is highly effective, which is this line on the far right. Okay? So this is what I put screen. When you take the rest of them are able to process 1 petabyte and more. But on some of them, you'd spend too much. That's it. That's all I wanted to say. So your separation is either horizontal or vertical.
Okay. Yeah. Just look at the position where you put those logos. You're looking at it half terabyte for Amazon Redshift, probably $1.5 million if you use Redshift. But for Google BigQuery, maybe you just spend $500,000. I mean, just position wise of those logos. Just show me that.
Yeah. The whole idea is to demonstrate that selecting the right technology for specific uses is crucial. For example, if you need 24/7 clusters, so this makes sense, and this will not. But if you're hardly analyzing your data, this will never make sense, and this will always make sense because you're not paying here anything but storage costs. This also can happen in specific use cases. You have 1 petabyte of archive data, and you maybe in the future might want to process it. Does it make sense?
Yeah. This one is called SQream. I don't know this system. Who owns that product, or are there a lot of customers on it? For you heard about the rest of the 4 of the technologies all over the place. But that SQream,
you know how many databases worldwide exist, which are in the top? About 200.
Okay.
You know which one you are minded to? The one who spent the most on marketing. And which passed the $1 billion marker in terms of revenue.
Mhm.
I know. I mean, I personally know a very long list of databases, and some of them are even fit to put in this very nice discussion. However, there's a limit on how much I can talk about magnificent technologies without reaching to a point. And the point I wanted to reach here, as you can clearly state in this framework, see in this framework, that there are technologies for every use case. So my question for you, when you have a petabyte use case, what are you trying to process with the data? What are you trying to achieve? So this list of 5 technologies kind of illustrates the degrees of freedom on which you have as an architect on what you are trying to achieve. I mean, there are other technologies, we can evaluate them, we can position them on these 4 quadrants, and everything will be clear. But the whole idea of these 4 sessions is to give you some sort of a framework when you are evaluating or experimenting with a new technology, and you have a very large data set, and you don't want to be lost in the marketing content, which is overwhelming. I can assure you it took me years of consult to achieve this degree of the confidence in this set of lectures. I mean, imagine how many use cases I need to be involved in just to be able to discuss about this with confidence.
Yeah.
Any more questions?
I have not exactly a question, but like to me, it would make a lot more sense to have this chart, but showing spend versus performance, right? Because like I understand the point that you're saying, okay, some
Let's try to build
solutions
it.
can handle bigger volumes, but trying to compare the same. Okay, so if I'm
Let's
doing
do
the
that.
same use case, yeah, this is
This
this is
is
what I said. It's
why
not exactly a question, but it is like a kind of what I wonder.
I respect you enough to make changes in my lecture.
Thank you
How's
so
that?
much. Highly appreciate.
Spend 1 second. I cannot think and talk and write, although I'm quite capable. Spend versus volume. Volume. Okay. Let's make it bold and underline so it will be clear. Underline so it will be clear. And let's do this again. And you wanted to compare spend versus performance?
Yeah, or speed, performance or speed. Yeah, for the same use case exactly. I think this is in the end, like this is what we are trying to say. Okay, what will perform better on the same use case, on the use case that we have here.
But the use case here is ad hoc analysis, and a different use case would be.
It's always a different use case is
yeah,
different.
I understand.
I get the point there, but again,
okay,
trying to think like like apples and apples.
Yeah. I understand. Let's see. Okay. So essentially, we are talking about time to process, right? And the units would be days.
Je comprends pas. C'est quoi le truc là?
Hours, seconds.
Tiens, le truc là.
And
19 heures.
If you're not talking, please mute yourself. Thank you. So let me think. For 10 analysts, given these technologies, so to be clear and fair, when we talk about ad hoc query, waiting 30 seconds or 40 seconds is the same for me. So we are talking about simply a resolution of seconds, minutes, hours. Why am I saying hours and not minutes? Because we have the benchmark I talked about, the 5.4 trillion records. Okay, so now it will be easier to compare. So if we are talking about the seconds, it will be doable by everybody. Everybody will be able to compete in the power queries of 1 second, but there's a big trade-off. Okay? Meaning if we're talking about seconds, everything will be fast enough using these 5 technologies, but naturally each one will differ a little bit. One would be faster than the other in specific scenarios. And the crux of it would be that you won't even know that in a different use case, another technology would be faster or slower. So it's not a clear cut. However, the questions remain, the question you should be asking yourself, sorry, that is the TCO analysis giving power queries of seconds on a bigger data set. So assuming you want to achieve a sub-second performance using petabyte of data, which I'm not saying it's possible or not, that depends highly on the type of query. I mean, you cannot do ad hoc query on 1 petabyte or full scan and expect sub-second, right? So it doesn't make sense. So you won't be able to do this on this one, but we could say the following. So if we are talking about embedded BI, where you would expect sub-second, there will be give or take in 1 second, 2, 3, 4, 5 seconds. Let's make it, you know what? Let's make it like this. Smaller, what? Smaller equal 10 seconds. They are more or less equal, okay? If you're talking about ad hoc query, you're talking about the hours. So this means you need to put this one here, and Snowflake would be expensive, and Redshift would be expensive, and Databricks, BigQuery would make sense over here. Meaning achieving the same performance target would cost here more, here less, but this will scale for more data in the same minutes. So essentially, we don't have that data access, so let's put it here, okay? So it will be very comparable, okay? So the ROI TCO analysis will be somewhere around here. Okay? If you're talking about minutes, so let's put that here. If you're talking about scenarios where you have power queries over hours, this would be the case. Meaning what? You won't spend more by using SQream, and you'll be able to process more data in the same time frame. It means you'll be spending more time on these technologies. Because the bigger the data sets, the more powerful the query, and the more long-lasting, the more advantage you'll have for a more powerful solution. But it's becoming less attractive when you talk about the less than 10 seconds. So why did I mention this for the embedded use case? Because if you talk about sub-second, whoops, these you will be spending more. And the reason for that is because, this one has a feature that allows you to pre-compile your query. The reason it takes more time to process a very short query in an analytical solution, which is all these solutions, is because the compiler takes a couple of seconds just to process your query before processing your data. So when you discuss less than 1 second performance target, it becomes a different ballgame. You need to talk about milliseconds. You need to cut down from your processing time. So essentially it becomes a problem of optimizing the compilation time as well of the query. So essentially, the only technology I know offers this feature of pre-compiling your query, saving in it, and only running it when you need it. This is exactly an embedded BI use case. Does this answer your question, Uwe?
Yeah, thank you.
I could have maybe, no, let's stop here. Any questions? Okay, so guys, to sum up, it's simply a matter of balancing between your ROI, cost, and performance target. I won't do the pop quiz. Let's skip it for now. In the end of the day, your job as a data engineer is to balance between this concept of this framework. I hope you'll find it useful. Call to action, you're more than welcome to read our blogs. I would be very much happy if you could join our YouTube channel and subscribe. And it will only help me just spreading the word. There's no commercial benefits behind it, even though I'm a paid consultant. This section of my job is just for fun. So I would be honored if you would just like and share the community, and you're more than welcome to stay in contact and ask questions. Unless there are any more questions, guys, we're done.
I got a question,
Please.
but maybe hope it's not too late. It's still relating to the cost, let's say, issue. Isn't it changing over time? Like I heard, like people starting pushing the data into Google BigQuery, then it became more costly. Then they just pulling out, putting somewhere else. Is it like thing you see? It's more frequently changing, or it's like more or less stable?
It depends. Some scenarios do not expect growth rate, and some expect incorrect growth rate. So essentially, it really depends on the life cycle of your company. If you're just starting out as a startup, and on day one you expect to gather 1 petabyte of data, then you need to be very, very, very careful. But if you just started and you have no way of predicting, let's go back. But you know you're going to collect data, okay? So all you know, all you can assess, generally speaking, is your volume. So you can naturally do a quick TCO analysis and understand where you are on the scale of cost. So technologies like BigQuery will be very cost effective. The same goes for Databricks. No, it will be a bit more expensive, but generally speaking, to your first 100 terabyte, you're good to go. When you're growing, exceeding the 100 terabyte, and you have prediction to exceed that over the next years, now is the time to reevaluate your petascale architecture. Unless you pass the 100 terabyte mark, there's really no point of reevaluating your technology, because the amount of engineering effort required is massive. So imagine you switch your technology every year. It's too much work. You want to focus on insights, not your cost of infrastructure. Let me see if I can add a slide here that maybe simplify your life.
Okay, thank you. Yeah. Okay, so it also means like there is like a life cycle also. And company starts usually, let's say, in the beginning, some initial historical data, and then it grows and grows and grows. So then you start to realize it's costing you too much to query the data, and then you change the technology. Yeah,
so, I mean, let me, since you asked, so essentially, when you start out and you never handle the big data use case, you would expect no knee problems. So essentially, 1 terabyte, 10 terabyte, 100, 1,000, it's all the same for you. Most engineers would say, what? Just store more resources and it will work. And you expect a theoretical running time, which is linear. The more data you have, the more you grow. But essentially, the problems, the reality is that you have a new problem every 10x of your scale, meaning until 1 terabyte, this is more or less your infrastructure capabilities, and there's a new problem there. When you scale up to 10 terabyte, again, you switch technology and there's a new problem and you scale again. And when you switch to 100 terabyte, again, you do your magic and it scales, and then you are ready for the 1 terabyte scale. But I wouldn't recommend to companies to design on day one all the way to 1 petabyte unless they expect in the next year or two to be there. If it's clear you're going to be there from day one, plan for this one. If you're not sure, guesstimate. It's a combination of guess and estimate. A ballpark number. If you're not sure, use an architect. Call me. Ask me what I think. For 5 minutes, I'll give you 5 minutes of consult for free. You know what? I'll give you even more because you're a community member. And I'd like to converse with you guys. But the whole idea is not to overplan in terms of engineering, but match the right technology for your use case. So if you're assessing a petascale, naturally this slide applies. If you're assessing an embedded BI and a sub-second latency, this slide applies. And probably other technologies will be applicable. If you're talking about queries that will talk hours because it's research, and naturally everything changes. Okay? Does it make sense?
Yeah, absolutely. The question is always, with change on every technology, you have to implement. That means you have to pay more salary to the engineers, and you have to,
yes.
to train people, and so on and so forth.
Yes. This is partly why I always have a job. This is partly why I'm free to do consults, because I have so much job. I don't need to worry about anyone doing their own job using my recommendation from the meetups. I would be more than honored to find out that someone finds this useful in their day-to-day job.
Yeah. Thank you very much. It's very, very good explanation. Fantastic.
Okay, thank you. Questions from the audience. Is it really big data? Perhaps it's time for terminology to be updated. Very good comment, actually. Remember this slide? We briefed into it quickly. So this is a question by Lawrence. And it's a lesson. 1 terabyte, it's really big data problem. So allow me to give you, since I like you too much, my definition of a big data problem. You have a big data problem when your infrastructure fails on a regular basis to process the amount of data you have in your system, period. So essentially, if we're going back to the slide I just added to Miko's question, which is perfect in my eyes, you have a big data problem when the technology doesn't match the ability to process the amount of data. So I can show you a big data problem on just 1 terabyte. Complex processing computational problem, so massive that it will break any technology on only given 1 terabyte of data. So when you talk about big data, for my eyes, it's not a problem of definition or technology, just a matter of paradigm and methodology, how you approach a problem. So essentially, it doesn't matter how much your data set is big. What matters is the inflection point, the point where the technology is unable to effectively process the data. I hope it answers your question. Thanks you for your feedback, Giligo, on any other questions? The Titan, my first petascale architecture. What is the link to part? Oh, okay. If you want the link, yeah, sure, no problem. Small remark: if you RSVP DS to the meetup, you'll get an email about this link with the updated video of part 4. But I just put part 1 to 3 in the chat, and you can go back to the website of Big Data Demystified. You can easily find that in Google, data engineering, architecture, and you will find it over here. Any more questions? Please. Okay, to sum up, people, it was a very nice experience to talk to you guys. I really enjoyed preparing this content and talking to you about the petascale architecture. If you have more needs around data and more ideas for content, you're more than welcome to send it to me. I will see if I can come up with something interesting for all of us. For now, thank you for your time. I hope you will enjoy the last 8 hours of this content, and I look forward to the next time we meet again. And feel free to contact me if you have a petascale architecture problem, big data problem, whatever you do, wherever you work. I will be more than happy to engage with you and help you solve your challenges. For me and my team, thank you all for joining, and I look forward to see you again in this community.